So hello everyone. So today we'll be discussing a topic which is called as design of footing for column with moment. So I'm going to write it down. Design of footing for column with. So what are the given data? The given data is that the column size is 300 by 500 mm. 300 by 500. The axial load is, if I consider it as P, it is given as 400 kilonewton. Then the moment is given as 35 kilonewton meter. Okay. Then safe bearing capacity of soil is given as 120 kilonewton per meter square. And materials are given as M20 concrete and Fe 500 steel. Okay, so let us start with the solution. So first what we have to do is we have to do the sizing. Okay, now when the load given to us is 400 kilonewton, we also have to take into account the self weight. Okay, self weight. Now we cannot calculate the self weight here exactly, so we take it as 10% of the load. It is like an approximation. Okay, so it will become 40 kilonewton. So total will become 440 kilonewton. Okay, now when there is a moment along with an axial load, okay, then actually the stress is a little bit different. Okay, the stress calculation. Okay, so if I try to write the formula for pressure, under a footing, when there is a moment, the pressure value is actually this one, W by A plus minus M by Z. Suppose this is the footing. So the pressure will be like this. It will not be uniform, it will be non-uniform. So here it will be W by A plus M by Z. And here will be W by A minus M by Z. So it will be different when there is a both moment and axial load. So this we have to calculate. Okay, this we have to calculate. Now let us again go back. This load, the moment is given as 35 kilonewton meter, and the load that was given was 400 kilonewton. So from here we get to find the eccentricity, which is equal to M by P, which is equal to 35 by 400. It's around 0.0875, or we can say 87.5 mm. So this E should be less than or equal to 1/6 of the length of the footing. Okay, so if this situation is satisfied, then the corresponding length we can provide. Okay, so now let us do the sizing of the footing. So area required is equal to the total load including self weight, which is 440, by safe bearing capacity, which is 120. Generally, if there is a only axial load, then we simply do it like this. Okay, we take the load including self weight, okay, divided by SBC. But if there is a moment, we take a multiplication factor of 1.15 also. Okay, it is a factor which is taken to account for the moment. Okay, but if there is no moment like this in this numerical, then 35 kilonewton meter moment was there. But if there is no moment, then we don't take this 1.15. But if there is a moment, then we take this factor. So how much does it come? Let me just check. 440 by 120 into 1.15. So it comes around 4.21 meter square. So let us take a length which is like dimension of the footing in this manner. Let us take a little bit higher. Let us take length 2.5 meter and width 1.8 meter for the footing. So the area provided becomes 2.5 into 1.8, which is equal to 4.5 meter square. So area 4.5 meter square. Okay, so let us now proceed. We knew that the pressure was equal to W by A, load by area, plus minus moment by Z. Z is the section modulus. Okay, so area we have got 4.5 meter square. Z we have taken, Z will be what? BD square by 6. BD square by 6. Okay, this is the formula, standard formula for the section modulus. So B is, or in this case, it is like BL square by 6. Okay, so it becomes 1.8 for the footing into 2.5 as we have considered these two values by 6. So it becomes 1.875 meter cube. Let me just recheck the values. 1.8 into 2.5 square by 6, 1.875 meter cube. So the value, one will be Q max and one will be Q minimum. So Q max will be the load 400 by area 4.5 plus 35 moment by 1.875, and Q minimum will be 400 by 4.5 minus 35 by 1.875. Let me find out these two values now. So 400 by 4.5 plus 35 by 1.875, it becomes 107.55. and the minimum one is 70.22. Okay, the minimum one is 70.22. Now the maximum soil pressure, Qmax, is actually less than the SBC, which is SBC was how much? 120. So we can say that it is a okay condition. Okay, so maximum pressure is less than the SBC of the soil. That means the capacity of the soil. So it's fine. Okay, now let us directly go into the design phase. Okay, now let us go into the design phase. So for design condition, the load that we will be taking is the axial load that we will be taking will be factored one. So the P will become 400 into 1.5 is equal to 600. And the moment will be taking as factored, which is 35 into 1.5, which is equal to 52.5 kilonewton meter. Okay, so now using this, we update the pressure values. So Qmax will be 600 by area, which is 4.5 plus 52.5 by 1.875, which is equal to 161.33 kilonewton per meter square. And Q minimum 600 by 4.5 minus 52.5 by 1.875, which is equal to 105.33 kilonewton per meter square. So if I try to draw this, okay, in the like in order for you to visualize it much properly, how will it look like? This is the footing. So this will be like 161.33, 161.33. Then next is here on the right side, it will be 105.33. Okay, let me just recheck the values. 161.33 and 105.33. Now, what will you do here? Using this pressure values, we have to find out the bending moment in the footing. So for the bending moment in the footing, we always consider the bending moment at the face of the column. Okay, so for this, we divide it into two parts. Okay, this area, because we consider the bending moment either from the left or the right, so we'll consider the left part for finding out the bending moment. Okay, so I'm considering this as area 1 and this one as area 2. Okay, now we also have to know what is the pressure at this section. What is the pressure at this section? 161.33 we have got. and 105.33 it is there on the other side. So if I have to find out the pressure here, then we can simply do the unitary method. So unitary method will be 161.33 minus 161.33 minus 105.33. This is the change that is happening along a length of 2.5 meter. So what will be the change that will be there along a length of 1 meter? Okay, in a length of 2.5 meter, the change is 160, the difference between this 161.33 to 105.33. That is the difference of pressure, that is the change that happened along a length of 2.5 meters. So along a length of 1 meter, what is the difference? So in that way, we will be calculating the value here at the surface. So let me just calculate 0.33 minus 105.33 by 2.5, 138.93. 93 kilonewton per meter square. Okay, so that means 161.33 changed to 105.33 to difference we got divided by 2.5. This was 2.5. So along a length of 1 meter, we have found out the value. It is 138.93. So now we'll be finding out the moment using these values. Now if I try to maximize this part, just I'm drawing it in a much more bigger way. So this area 1, if I consider this area 1, so how will we calculate the moment? So width we know it is B into the length is 1, 1, 1 into the value that is here is 138.93. Isn't it? 138.93. So we multiply this 138.93. It is constant throughout. 138.93 is constant throughout. So width into this one is the area, this one is the pressure. So it gives us the load, and the load is falling through the center. That means it is falling like this through the center because it is a constant. So the distance of the point of action of the load from this section is 0.5. So this is how we get the moment due to this area 1. Now what happens for the area 2? If I draw it here, just I'm drawing the area 2 only. So this one is 1. This one is now how much? 161.33 minus 138.93. This part, isn't it? So this area 2, the load falls from a distance of 2/3 of 1 CZ of the load. Okay, resultant load. So now we'll be doing the calculation here. So area is B into 1, width into length. into, since it is a triangular load, so we'll be doing the half into base into altitude. Half into altitude is base is 1 into altitude is 161.33 minus 138.93 into 2 by 3. This will give us the moment. Okay, so in this way we calculate the moment. This one is the moment due to the, and B is 1.8 meter. So this one is the moment due to the triangular part, and earlier we have already got the moment due to the rectangular part. Okay, so I'll just write the whole equation once. Okay, so moment will become B into 1 into 138.93 into half. Okay, this is the area, this is the pressure. Ultimately, this will become the whole load into the distance of the point of action of the load to the face of the column is half. Okay, plus for the triangular section, it is B into 1 into this is the area, and the pressure is half into base into altitude. Since it is a triangular load, 0.33 minus 138.93 into 1 into this one. So area into this pressure becomes the whole load. Okay, so this one is the value. Okay, this is the required equation for the moment. And how much we get? B is 1.8, as I have already told. We get it around 138.47 kilonewton meter. Okay, 138.47 kilonewton meter. So now if I have this moment, we can calculate the area of steel, right? So let us move on with the calculation. Let us assume an effective depth of 450 mm. Now, what will be the area of steel? Moment we have already got. Area of steel formula, as usual. This one. We'll write down the formula along with the values. Four point six into 138.47 into 10 to the power 6 by secant 20 into, which is 1800. We keep everything in mm. D square for 450 mm square into 1800 into 450. Okay, so ultimately we calculate it and we get the AST value around 721 mm square. Okay, now we have to check whether it is like more than or less than the minimum AST. Okay, so minimum AST is 0.12%. So we'll check it 0.12 by 100 into 1800 in 0 width into depth overall depth 500. And how much it is coming? It is 1080 mm square. So this much we have to provide anyway. Okay, I'll just check the value 0.012, 0.0012 into 1800 into 500. Yes, this much we have to provide anyway. Okay, so you take 12 mm dia bars. Okay, suppose 12 mm dia bars you take. So how many number of bars you require? Number of bars is equal to 1080 by pi into 12 square by 4. So I'll calculate it. 1080 divided by pi into 12 12 square 9.54. So like it is around 10 bars. So that is the end of the problem. Thank you.